but it was not much time to comment. So this was the solution of the logarithmic plasma equilibrium equation, and this F is related to confinement potential. So if it is standard Wigner-Dyson, then this F is linear function, but this expression is valid for any F, and I deliberately derived it because now we can consider what happens if this confinement potential is not quadratic but some function of the energy. So basically I told you that if it is a linear function, then this integral is independent of the variable e, and we have a semicircle. But if this function is not linear, and for instance it is linear with some quadratic correction or cubic correction, or it is, let's say, quadratic function from the very beginning, or cubic function, any function, power function, then we can analyze this integral, and we can see that there are two different regimes, and one regime is when so-called strong confinement, when this alpha is greater than 1, and then what happens is that if alpha is greater than 1, then the derivative is a power, a positive power, and when it is a positive power, then if I send limits of integration to infinity and look at this integrand when this e is smaller than d goes to infinity, so then there is a function like f of t prime divided by e prime minus e, and this function should be integrated. And this function can be this integral from minus infinity to plus infinity of this part could be divergent and could be convergent. If it is divergent, then I cannot then this integral when d goes to infinity first doesn't make sense because the integral is divergent. This means that I cannot send d to infinity, I have to keep it finite. And what means keep finite means that the region of integration close to d makes the main contribution. And in this situation, the solution looks qualitatively like a semicircle, though it is not a semicircle because the value of the density at 0 is proportional to n1 minus 1 over alpha, and the bandwidth, this d, is proportional to n1 over alpha, where n is size of the matrix. So for the semicircle, alpha is equal to 2, and we have this square root of n and this square root of n. So it is indeed a semicircle. The radius here is equal to the radius here. Okay, what is important for such densities is that close to the center, if I have a narrow window in the energy, then this density is always a constant. It is almost a constant. And this means that actually I do not have, if I want to work in a small window, I don't have to do what is called unfolding. I will explain what is it later. So important is that the density here in the small window is almost constant. But other situation is when this integral f of e together with this factor, when it is convergent at infinity when d goes to infinity. And this means the following, that that this integral is dominated by e independent of d of the order of lambda, let's say, and this means that I can safely send d to infinity if I mean to take advantage of the following, that this e is much smaller than d, and then I can take this root out of the integral, and the remaining part is convergent, and it is of the order, I mean, it is qualitatively like a power law in this region where E is large compared to 1, but it is small compared to the bandwidth. So in this region between unity and the bandwidth, it behaves like that. So what is important is that now, even though the density is finite here, it is independent of the matrix size. So here it grows with the matrix size, and here it is independent. So what means this growth means the following, that if I increase the number of levels, so confinement makes them accumulated near the center, as well as makes, I mean, it is not full confinement, therefore levels are of course spread along the axis, like this curve corresponds to larger n than this one, so there is a spreading, but also there is an accumulation. And here there is no accumulation. There is part of the density does not depend on the size of matrix, and there is only the spreading, and this spreading becomes actually very fast, because if alpha is small, then it is a big power. So that is what happens, and it appears that this is a sort of phase transition, in the sense that there is a qualitative change of the behavior. So then people can study the correlation functions of the density, and show that the correlation functions of the density are anomalous in this region. Anomalous means that they don't behave like in this case, or in the case where confinement potential is quadratic. So this is two cases, and then there is even more interesting case where the confinement becomes so shallow that it is logarithmic, so it behaves like log. I put here log squared, but in fact one can put here some power of the log and also find the solution. And for the log squared, the easiest way to find the solution is just to write this log like a limit of alpha going to 0, and then square it, and then plug into this formula, which was derived already. And the result is the following, that the density in the region for the energy is much bigger than 1, but much smaller than the bandwidth. It behaves like 1 over E. So if here is a power greater than 2, then there will be additional log in log E in the numerator. But this, when it is log squared, then it is a pure power, but power is -1. And then what happens is that now the confinement potential is so shallow, so weak, that if I add more levels, increase the size of the system, then this bandwidth becomes exponentially large. So it was a power law large for alpha bigger than 1, but when alpha goes to 0, it becomes exponentially large. And this is also an indication of another phase transition, in the sense that alpha, if alpha equal to 0, so we have some logarithmic confinement, then not only levels run away very far, but also all the correlation functions change very dramatically. I will show you what happens in this case later on. So this is how things depend on the confinement potential. So now I want again to use this plasma equation and derive the behavior of spacing distribution when the spacing is large. So I told you that the spacing distribution looks like this. This is P of S and this is spacing, and we have derived by elementary means that here the behavior is S to beta, where beta is 1, 2 or 4, and now I want to derive what happens here, where the spacing is much bigger than the mean. So what does it mean spacing is large? When spacing is large, this means the following, that your density made of levels, of dense levels here, but there is a gap, the gap which is much bigger than the mean level spacing. So the mean level spacing in the plasma model is considered to be the smallest parameter, but then if I want to consider what is the distribution at large spacing, much larger than the mean, then I have to find the solution of the same plasma equation, but with additional condition that that there is a gap which width is omega. So omega means if I want to study the distribution function here where S is equal omega by mean level spacing, this is what I'm going to do. So this is amazingly, this can be done again with the same plasma equation, but in this case I have to impose the condition that there is a gap. And it appears that this integral equation has solutions, and they are known, but they are classified by the number of gaps you have in the solution. So if I say that there is no gap, then the solution was like I have shown you last time. If I say that there is one gap, then the solution is a bit more complicated, because now it contains two parameters. One of them is the bandwidth, and the other is the gap. So I will this time I will not be showing you that this is a solution, but if you face equations like this plasma equation for logarithmic interaction between particles, then you should know that such integral equation is exactly solvable, and the solution essentially contains some square roots, but now two square roots, one which is describing the end of the spectrum, and the other square root which describes what happens near the gap. So, okay, believe me that this is a correct solution, and remember for future that such integral equations are exactly solvable, because this situation with logarithmically interacting particles or vortices or whatever, they are very frequent situation in physics. Okay, so this is the general solution for any size of the matrix, for any omega. But now what I have to do in order to compute this probability distribution, I have to use Boltzmann statistics, because this is a classical plasma, and Boltzmann statistics says that the probability is exponential minus beta. Beta is in like inverse temperature of this classical plasma, and this is the difference between the energy with the gap and energy without the gap. So energy without the gap is semicircle, which should be substituted into this into here. This is the energy functional, and so if I solve this equation without the gap and then put the solution here, this will be the energy without the gap. But then if I solve this equation provided that there is a gap, it will be a different solution, as I have shown to you, and I have to plug into here and find the difference between these two elements. And in fact, what one can do using the fact that I'm dealing with the solutions of plasma equations, I can cast the difference in the energy in the following convenient way. So this is, this is a matter of exclusion of confinement potential from the equation. So you see the energy depends on the confinement potential, but the solution also depends on the confinement potential. And so what you can do, you can exclude this term and operate only with this one. And this is exactly, and this exclusion is done with the help of this equation, and the result is like this. So the difference in the energy is a function of the difference in the solution. So this is solution with the gap, this is solution without the gap. So this is the first term, and the integration goes along the region outside the gap. So this C is this and this. But then there is a path inside this gap, where integration goes inside the gap, and also, of course, there is this logarithmic term, and here stands only the solution without the gap, because the solution with the gap is exactly equal to 0. So this is such exact formula, and then what I have to do, I have to show, I have to analyze how does this thing depend on omega. Because if I find how does it depend on omega, then I can put it into here, and then I can say what is the probability density to find spacing on this tape. So this analysis actually is quite simple to do, because first of all, when we inspect this solution, we will see that this is the exact plot of this solution, and what you can see the following, that in this region, close to the gap, the solution looks like this. You can obtain this approximate formula, and because, as I said, this is a strong confinement, and when there is a strong confinement here, this part is almost flat. So here it is not, because the difference in the scale is 30. So this is the spectrum bandwidth, and this is the gap. But when this difference is not 30, but let's say 300 or 3000 or even more, then this part will be almost flat, and then the solution will look like this. So this is the limit where n goes to infinity. So first of all, if you look at this solution, you will see the following, that when you impose the gap, then the plasma particles or levels, they accumulate here near the edge of the gap. And this form of the solution and this accumulation near the end of the gap, it happens in many situations. For instance, if you study superconducting properties, how superconducting photoparameter depends on the energy, you know that when there is a superconductivity, then there is a gap in the spectrum, and it is also the formula like this. So if you make a gap, then the particles are accumulated here. Okay, so
Sorry. shouldn't in first term in delta epsilon, shouldn't there be something like rho 0?
First term here.
Yes. Shouldn't it be like rho 0 multiplied by delta rho?
This one. No.
No. First term. Yes,
This.
but instead of 1 of delta rho, it should be rho 0, no?
No. Should be the difference, because I'm finding the difference in the energy.
Yes.
So the difference in the energy should be small and go to 0 when omega goes to 0. When the gap collapses, this difference should go to 0. And here it goes to 0 because of the limits of integration. And here it goes to 0 because this difference becomes 0.
Yes, but only one of those terms should be delta rho. The second one should be rho 0, no?
Both terms should be taken into account.
No. First multiplier. I mean, it should be.
First derivative.
It should be something like. It should be something like this.
No.
Okay.
No, it is like this.
Okay.
No, such term cannot be present, I tell you why. Because this is an equilibrium plasma. And when we are in the equilibrium, the first variational derivative is equal to 0.
Okay.
And only the second one may appear. Okay. So now, if I take into account this approximate relation which comes from here when d goes is much bigger than the gap, then the simplest way to analyze is just to make a rescaling. Say that E is rescaled like this with omega, and E prime is rescaled like this with omega. And when I put this rescaling to here, first of all, what I will get omega squared because of these two measures. So this will be proportional to omega, and this will be proportional to omega. So I will get omega squared, and here too, I also get omega squared. So the overall result is first of all proportional to omega squared. But then, when I make a rescaling here, there will be log omega. So, and also here there will be log omega. So, therefore, there will be log omega taken separately, and also log of x minus y, and this gives something of order 1. So, then the overall form of this delta E is omega squared because of two measures, and then constant plus independent of omega plus another constant times log omega. So basically there are two terms, omega and omega log omega. Now I will show that this term is not present. Why it is not present? Because if, as I said, I make rescaling and then take separately the term which is proportional to log omega, then this log omega is out, and here the same thing, log omega is out, and what is this coefficient b? It will be simply the integral like this, because if log omega is taken away and the other term x minus y contributes to here, then I have this thing from here and this thing from here. And now I show that they must be equal to each other. Why they must be equal to each other? Because the total number of particles, the total number of levels does not change. So when I make a gap, so when I make a gap, they are redistributed, but they are not changed. And this conservation of the number of levels mm, uh, can be written in the following way, that the number of levels without the gap is rho naught integrated over exterior of the gap, and then rho naught integrated over the region of the gap. This is without the gap. And with the gap, it is only rho integrated over exterior of the gap. So this is the difference between the number of levels, and it should be equal to 0. But then, if this is equal to 0, I can see that this guy is also equal to 0, because delta rho is this guy, and rho naught is here, so I have this b equal to 0. So what I will obtain that this delta E, which stays here, is proportional to omega squared. And therefore, I can immediately say that this behavior here is minus something, some coefficient, let's say A times omega squared. What I want to tell you is the following, that this derivation, why I showed it to you, because this derivation shows that this omega squared is basically coming from the measure of integration. So omega, one omega from here, the other from here, so here too. So this means that if I take any confinement potential which is with a strong confinement, such that this formula is true, because it is true only for the strong confinement. If you see what happens at E much bigger than the gap, this is a constant. So, and this constant is what I told you is the feature of the strong confinement. So if there is a strong confinement, this is a correct approximate formula for E of the order of omega, and much smaller than the bandwidth, and then you will get E to minus omega squared in any case. So this E to minus omega squared is not a consequence of the Gaussian distribution of matrix elements. It's not a consequence that confinement potential is quadratic. You can take confinement potential to the fourth power and it will be the same result. So therefore, when people sometimes derive this form just using 2 by 2 matrix, then of course they also get a Gaussian thing, but only in the case where the matrix elements are Gaussian distributed. So this 2 by 2 derivation, which I have also shown to you, it is good for small spacing, but it is cheating for large spacing. Because cheating in the sense that that this result is for any confinement potential which is strong. So now what remains to do is to compute this constant A, and it is with such a form it is possible to compute it exactly, and the result is pi squared over 16, and of course rho naught will be the prefactor here and here. So this is the answer. And now collecting everything. So this is the asymptotic behavior at the tail of the spacing distribution for any strong confinement. You see here stands the beta, which is 1, 2, or 4, and it comes from the Boltzmann distribution. Okay, so of course, if the confinement is not strong, then things change, and it changes because this is no longer valid. So then, one has to rederive it, and it is possible to rederive for a weak confinement as well. I will not bother you with this calculation, but you know how it is in principle possible to do. And now, when we know this asymptotics and we know this asymptotics, one can combine them together and guess S to beta e to minus omega or S is they are proportional S squared, and this is so-called Wigner surmise. This is not an exact formula at all. This is simply a combination of the behavior here and the behavior there. And this Wigner surmise looks like that. And there are two conditions. One condition is that this is the probability density. If I integrate the probability density, it should be equal to 1, because if I integrate sum all the probability, there will be a probability of 1. And then the second thing is that S is omega by mean level spacing, and this means that the average spacing should be also 1. And then there are two constants and two conditions, and one can derive both constants, and this will be what is called Wigner surmise. And it is very sort of naive way of obtaining the form of the spacing distribution, but it appears that this naive way is rather close to the exact one. So, for instance, take this coefficient b. For beta equal to this accuracy of this Wigner surmise is the largest. So the exact b is equal to 1.24, and the one which you get from here is 1.27. So it is really very close. If you draw the entire distribution, it will be also very close everywhere. If you take other values of b, then there will be more discrepancy, especially for the case b equal 1, then these two things already significantly different. But the problem of computing the exact distribution, it goes beyond my scope. It actually is quite a complicated problem. One has to solve an integral equation, this time an integral equation which cannot be solved exactly, and so it can be written, but then one has to do numerical calculation and get all these constants and the entire shape. But luckily, this simple combination of the asymptotics at small s and at large s, and these two conditions, they give very good result.
Vladimir, I wonder for the exact solution you cannot write down the equation, right? But
I can write down only the integral equation which
Yes.
you know.
yes, but since we have these asymptotics, like, how can it even be different? So the exact solution, I don't know, would be some.
No, it is simply, you know, it is simply a matter of luck. So what I have derived for you, I have derived this asymptotics, right? And I, by considering 2 by 2 matrix, I have derived this asymptotic. You were not here, but I did it. And now I derive this asymptotics at large. So usually, if you combine these two, you can get very big deviation from the exact solution. Here, luckily, the deviation is not big. So the reason for that, I don't know. So it is a matter of luck, because this is not an exact solution, and an exact solution is formulated in a completely different way. And so why this Wigner surmise work? I don't know. Anybody knows. So, but you know, as a rule of thumb, it works well. That is. Okay, now we are coming to the correlation function of the density of states. So we considered now the density profile, and now the correlation function. So the simplest correlation function is the average product of the density of states. And in order to get rid of some details of the model, it is convenient to normalize it by the product of the averages. And the density of states is represented through exact energy levels, and this is it. So let us study this correlation function. So first of all, I would like to show you the general properties of this correlation function. So the general properties are the following. So if you take this expression and plug it into here, so then what stands in numerator will be the sum over n and m of this delta function. But now let me do the following. Let me split this sum in two parts. So one part will be when m is equal to n, and the other part is all the rest. So why it is convenient to separate this part with n is equal to m? It is convenient because if n is equal to m, then I can say that n is e prime because of the delta function, and then I will have a delta function of e minus e prime. And this goes, this is deterministic stuff. I can take it away from the averaging, and what remains is the average density. So this means that this part with n is equal to m, it looks like this. So there is a delta function part in this correlation function, which is a self-correlation, where the energy is correlated with itself. N is equal to m. And then there is a part which is which is regular. This is a singular part, singular function, and then there is a regular part, and this regular part is also useful to represent. Okay, here of course I did again. So here there should be the product of the averages. Here there should be a product of the averages. Is corrected. And then some other part. So why it is convenient to do like this? It is for the following reason. When E and E prime are far away from each other, then we expect that the correlation function of the product is factorized. So the average of the product will be the product of the averages. So this means that they become independently fluctuating. So at large distance E minus E prime, you expect that there will be unity here. I mean, if I put here the correct product of the averages. And then there is a remaining part, which is the most interesting, the most interesting part of the story. And so if I collect all together, then I will get for this function, I will get the delta function, which is self-correlation. Then I get unity, which is a limit where E minus E prime goes to infinity. And then I have the function which tells me how I reach this limit. So this is an absolutely general consideration, and then there is an important thing. So once again, the number of levels does not fluctuate. Rho fluctuate because energies are fluctuating, but the number of levels does not fluctuate. It is conserved, and therefore the integral over rho, whatever is it, must be equal to n. It actually follows from this formula as well. If you take an integral, this will be 1, and the sum from 1 to n gives you n. Okay, so then let me do the following. So I consider the numerator, which means the R10 multiplied by the denominator. So I consider only the numerator. And when I consider only the numerator and integrate it over one of the variables, so I consider this guy and then integrate over E prime, let's say. The integration and averaging, they commute, they always commute. Therefore, I can put integration here. So when I put integration here, I make use of this normalization, and then this integral will be n, and it does not fluctuate, it goes outside the averaging, and then I will get this expression. And now you see that there is average row here, and there is average row here. It is not integrated, the integral is over the E prime, so it can be cancelled, and then I have the expression like this. So this expression reflects the normalization. But now I can make it even more transparent, getting rid of the singular term. So I plug it Rn from here, and then make integrate this delta function, then use when I substitute this unity here, I obtain again a normalization, and thereby this term will cancel, and the contribution of delta function gives me -1. So it is simply to substitute this guy to here. And so, since this function is already regular, it doesn't contain delta function or whatever, therefore it is simply the sum rule which follows from the normalization. But you should you should take in mind that when I have proven this sum rule, I always considered number of levels finite. So because at some points I made subtraction n minus n, so I cannot subtract infinity minus infinity. It is, nobody knows what is it, but if n minus n is 0. So this means that n must be constant in order to, it could be arbitrarily large, but should be constant. Now, then what one can do a further simplification, and if you see here, there is rho LH times d, and this combination I will call ds, and this is the new variable, and this new variable is chosen in such a way that the density in this new variable is 1, because here I can write 1, and any change of the variables is such that the density times dE is conserved. So this means that in these variables the density is 1. So somehow I rectify this semicircle or whatever and make the density equal to 1. And then I substitute this ds to here, and I obtain the following sum rule, which is known as normalization sum rule, and I told you that it is important in derivation of this sum rule that n is finite. And now so far absolutely general consideration. And now I want to show you a very simple but very instructive example. And this is an example of random diagonal matrix where there is diagonal entries distributed in such a way. So the distribution is flat. It is equal to 1 over n if the energy levels smaller than n over 2, and 0 when the energy levels are bigger than n over 2. And now I can compute the correlation function in a very simple way. I just use I use this definition of the rho, and I consider only the numerator. I consider only the numerator because the density, average density is 0, is 1. Average density is 1 when I consider such distribution. So I just plainly put it here, and this integral is simply averaging over En, and this integral is averaging over En when the distribution is flat. Now I do this. Yes, this N is not equal to M, and when N is equal to M, I separated this term. So, as in general case, I will get here here the delta function, and here I will get 1 plus y. And then, on the other hand, if I do this integration, what I will get each integral over E over En and Em will be equal to 1, and then I will have 1 over N squared, and then I have the number of terms, which is N squared minus N. So, and this contributes to the delta function. So what you see here is there is this 1, N squared by N squared, and the remaining part is this y. So the function y, it is minus 1 over n, but this minus 1 over n spreads from minus n over 2 to plus n over 2. Why? Because there is this restriction here. So what I see is the following: that if I integrate this y, so this is the general normalization summary. And now I check for this particular case. So I integrate, let's say, over S prime. And this integration is simply the area of this strip. So it is n by 1 over n, it is minus 1, as it should be. But if I do the following, if I first send n to infinity, so take a limit, then this function will be 0, and integrating 0, I will get 0. So this is the demonstration that that this normalization sum rule is only valid if n is finite. I cannot do the following: I cannot first send n to infinity and then integrate. These two procedures, integrating from minus infinity to plus infinity and taking n to infinity, they do not commute, and this one has to take in mind. And the situation where there is a certain sum rule which is valid for finite n, but is violated when n taken to infinity first, such situation is also frequent situation in physics, and it is known as anomaly. So there are different anomalies in physics, but all of them have the same origin, that you have some rule that is proven at finite end, but it involves integration, and integration at taken n to infinity are not generally commute. So what actually I will show you later on, why I have demonstrated this example. First of all, to show that it's a simple example that shows that two limits are not commute. But there is the other purpose. The other purpose is the following: that the sum rule is normally violated when you take n to infinity limit first. So this the generic situation is when it is violated. So this is not an exclusion. This is a general point. It could be violated very strongly, like here. It could be violated that it will be not just -1 but -0.9. But it is violated as a generic situation. But there is one exclusion, and one exclusion is Wigner-Dyson matrices. For the Wigner-Dyson matrices, taking n to infinity first and then integrate it will give you again -1, nothing will change. And this is for the following reason, that consider the plasma model, and there is a logarithmic interaction there of plasma. Plasma with logarithmic interaction is incompressible, so you cannot compress it. If the interaction would be power law with power smaller than 1, then it is compressible. But with log it is incompressible. And all this deficiency of the integral is because of the compressibility of the system of energy levels. And when it is incompressible, then this anomaly doesn't happen. So this is just, we will see what happens with Wigner-Dyson case later on, but but still I show you something about Wigner-Dyson right now. So you see the example of diagonal random matrix is an extreme example of localization. So in this situation, the particular localized on one side in real space, and this leads to the maximal violation of the normalization summary. So basically, the physics is such that if you have Wigner-Dyson, you don't have violation of the sum rule when you take n to infinity first. If you have the matrix model or physical model in which there is localization or even some localization, tendency to localization, some localization effects, not necessarily full localization. So you may have so-called critical states which are delocalized but not ergodic, then you immediately will have violation of the sum rule. So this violation of the sum rule is actually also the measure of localization effect. Okay, so now I want to last time to use this plasma model to show that it is possible to extract something else from this plasma model. And this mathematical trick which I will be using, it is actually useful, and could be used in other situations. So first of all, consider the density, average density. So when we have the distribution, the Boltzmann distribution, then the average is what? You have to integrate over all configuration of rho, all the functions of rho. So it is a functional integration here. So you have to sum over all possible functions. And then, of course, there is some denominator which ensures that if you average unity, you will get unity. So this is the Boltzmann averaging formula, and now I want to do the following. Now I want to here there is a this is a plasma model which I have shown you so many times, and there is a confinement potential here. And now let me ask a question. Suppose I make a variation of the confinement potential. So I choose V, I change V by V plus delta V. What will happen to E, and what will happen to E? I will have some delta E. And now what I want to do, I want and now what I want to do, I want to find the variation of the average when I do the variation of the confinement potential. So, okay, so then, this is, okay, so I want to do the variation of the average, which is linear in the variation of the confinement potential. So what I have to do, I have to replace V by V plus delta V, find the difference term here, and then expand everything in this delta V. So when this is a simple exercise, so when I change V by delta V, so I will have such a change in the energy. This is the change in the energy. So if I want to ask what will be the change in rho, so I have to differentiate it with respect to change in the energy and multiply by the change of the energy. When I differentiate this thing, I will get the same exponent, and then I have to write the difference in the energy, and it is like this because it is linear in rho. This beta is in fact absorbed because in the plasma model there is 1 over beta in front of. So and this is the normalization constant Z. So this is the first term when I find the variation of the numerator. And then there is a variation of the denominator. So if it is 1 over Z squared, and then the variation of the denominator. and you can easily see that it is like this. Now everything is cast in the following way. So there is, you see here, there is rho phi to prime. And there is the one averaging. So this means that it is proportional to the average rho and rho. Now, then here there are two averaging, and one is rho phi and the other is rho of E2 prime. So then I have the product of the averages. And then I have delta V staying here. So then I told you this is formality, that the variational derivative of the delta rho over E delta rho over E prime, it is delta of E minus E prime. So this is the rule of making the variational derivative. So when you take this delta E and divided by delta, I mean, it is already seen from here. So delta of rho, as I said, it is proportional to that, and this is delta of rho, and then there is delta V, and then given this delta function and integration over the E prime, you will get this formula. So this is a very general formula for Boltzmann statistics. So it is not only for that, it is for it is a very general formula for Boltzmann statistics. And actually, what it does, this formula relates the fluctuations and the linear response. So this is the linear response. So you have a quantity which is rho phi, and you want to know how it is changed when you change some potential here. So this is the linear response, and this is the fluctuation. So you know that in statistics there is fluctuation dissipation theorem. So it is similar to that, but there is no dissipation here. It is more easy. It is just the formality, and you see how fluctuation is related to the linear response. This is a general thing for such statistics. And then you see, I have a formula from the solution of the plasma model for this rho as a function of the confinement potential. So I can compute this derivative. So this is this formula, and so I put here this f of E, which is 1 over beta derivative with respect to E prime. 1 over beta is here, and now confinement potential is explicitly there, and I have to make the variation of that with respect to the confinement potential. So the result is the following. that if you if you want to compute such derivative, then you essentially have to have a derivative of that, delta V over E2 prime over delta E of 1 prime, and so you have a delta, you would have a delta function according to that. So here it is any function, so it's not necessarily rho, it could be V. So you have a delta function here, but because of this prime, you have a derivative of the delta function. Integral of derivative of the delta function is computed by integration by parts, so this means that it is minus derivative of the remaining part of the integral taking at P prime. So this is what appears to be, and then it is only to take this derivative over E prime and this is this derivative, so now I make some simplification. I told you that the bandwidth is extensive in the number of the particles, so if the bandwidth is much larger than both energies, so I can neglect E here and neglect E prime here, and E here cancel this this factor, and then I obtain a simple formula. And this was the derivative, but if I remember that that this fluctuation is proportional to this derivative with the sign minus, I will get this formula. So then, so you see what happens. What happens is that the irreducible average of two densities is in the Wigner-Dyson case, because I considered this Wigner-Dyson case, but with any potential, again, with any potential, I will get E minus E prime squared. So this thing is singular at E equals E prime, and this is because, as I told you, the plasma model does not distinguish, does not have a resolution of the mean level spacing. So it gives only some smooth envelope for scales much larger than the mean level spacing. And we will see later on that the true correlation function, irreducible correlation function, it is something like that. For instance, for unitary ensemble, it looks like this. And these oscillations are with a scale of mean level spacing, which is not seen in the plasma model. What plasma model sees, it sees only the envelope like this, and this envelope at E minus E prime much bigger than delta, and if I neglect oscillations, then I will get 1 over E minus E prime squared with the sign minus, end with a three-factor like this. So basically this is what plasma model can tell you not only about the semicircle, not only about what will be the density, the confining potential is strong or weak, but it also can tell you what will happen with the correlation function, but some rough features at scales much bigger than the mean level spacing. So this is